Greetings, chemistry students. Today we're going to talk about net ionic equations. And in order to get there, we're going to talk about what's first called a complete ionic equation. And so we're going to consider this reaction that's behind me on the board. It says lead 2 nitrate plus 2 potassium iodides make 2 potassium nitrates plus lead 2 iodide. And first of all, if we check the solubility rules, we'll notice that all nitrates are soluble. That's the first rule. So potassium nitrate is soluble. And then all chlorides, bromides, and iodides are soluble except silver, lead, and mercury too. So the lead 2 iodide is our precipitate. So we'll represent that with the letter S, meaning that it is solid or a precipitate that comes out of solution. So for a complete ionic equation, and you'll never have to actually write a complete ionic equation, you just need to know what these are. It shows all the particles in solution as they actually exist, where soluble ionic compounds are written as their individual ions. So if we go back and we look at this equation, well, lead nitrate, all nitrates are soluble. So we would break this apart into lead plus nitrates plus potassium ions plus iodide ions plus potassium ions plus nitrate ions plus the lead 2 iodide that stays together as a solid. So in other words, the complete ionic equation would say that lead with the plus 2 charge plus 2 nitrates plus 2 potassium ions plus 2 iodide ions makes 2 potassium ions plus 2 nitrate ions plus lead 2 iodide. Because all those other things would dissolve in solution. And with very few exceptions, these chemical reactions take place in solution. So that's a complete ionic equation. We pretty much never write these because of these things called spectator ions. Spectator ions are ions that essentially just watch, kind of like at an athletic event, spectators sit in the stands and watch. They generally don't go down onto the field or the court and participate in the game. That's a quick way to get kicked out of the game or arrested. So if we look at this, for instance, in our reaction here, the nitrates stay as part of the solution on both sides, and the potassiums stay as part of the solution on both sides. So potassium ions and nitrate ions are spectator ions, because what's happening in this reaction is that the lead is hooking up with the iodide to make lead 2 iodide. So the potassiums and the nitrates, they started floating around in solution, they finish floating around in solution, they're spectators. And so to get to a net ionic equation, what we will do is we will eliminate the spectator ions. So we'll take the nitrates and cross them out, and the potassiums and cross them out. And so our net ionic equation just says that lead 2 plus 2 iodides makes lead 2 iodide, like so. Now, essentially, for any double replacement reaction, all you do is on the product side, you have your precipitate, and on the reactant side, it's broken apart into its individual ions, right? So net ionic equations include only the ions that actually participate in the reaction, and we can write these for double replacement reactions that form precipitates or that form water. So I can show you a couple more examples of net ionic equations real quick. All right. If we take a look at this reaction, we have calcium chloride plus sodium sulfate makes calcium sulfate plus sodium chloride. If we check our solubility rules, we'll see that all sulfates are soluble except calcium, strontium, barium, mercury, lead, 2, and silver. So calcium sulfate is our precipitate. So to write a net ionic equation, on the product side, we're going to have calcium sulfate. And on the reactant side, we just break it apart into calcium ions and sulfate ions. Because essentially, in this reaction, when you put it into water, the calciums and the chlorides dissolve, the sodiums and the sulfates dissolve, and your reaction is the calciums and the sulfates come together and precipitate out, making calcium sulfate. The sodiums and the chlorides remain floating around in solution. We'll take a look at one more example. All right, in this reaction, we have hydrogen chloride reacting with sodium hydroxide to make hydrogen hydroxide and sodium chloride. Well, if we check our solubility rules, it says all hydroxides are insoluble except for group 1, strontium, barium, and ammonium. And then we know that sodium chloride is soluble because it's in group 1. But hydrogen's not really in group 1. So is hydrogen hydroxide soluble? Well, it's kind of a trick question because hydrogen hydroxide is liquid water. And water doesn't dissolve in water. It's a key thing to remember. Water doesn't dissolve in water. When you put water into water, you just get more water. And if you produce water, that is a way to make a reaction happen. So what happens in this reaction is you have the hydrogens and the chlorides floating around and the sodiums and the hydroxides floating around, and the hydrogen and the hydroxide come together and produce more water. So our net ionic equation produces water, and we break it apart as the hydrogens and the hydroxides that are what make this reaction happen. All right, guys, I've got some bonus content for you. You need to know the test for carbon dioxide. It's part of our curriculum. So I have this liquid right here. This is called Limewater. And all Limewater is, it's a very dilute solution of calcium hydroxide, which, according to your reference tables, is insoluble. However, a tiny amount of calcium hydroxide can dissolve into water, and so that's what I've got right here. Now, I will then, using this drinking straw, blow into the water, introducing carbon dioxide into it, and we'll see what happens. As you can see, this Limewater has turned cloudy or milky as it has produced the substance calcium carbonate, which is even less soluble. The test for carbon dioxide is that it turns Limewater this cloudy